So I'm just briefly going to talk about differentials in a way that kind of makes sense and makes everything in this chapter about differentials kind of make sense in the context of everything you've already learned in algebra and calculus. So you've already learned that if you have some continuous function, the slope of that function, or the slope of the tangent to that function at any point along it, is given by the derivative of that function. You also know by now that if f of x is the output of a function and x is the input, that y is the output. And that if f prime of x is the derivative, then dy by dx is the derivative. So now we'll go back in time to when you first learned slope. Slope is rise over run for any linear function. And rise is the change in y, and run is the change in x. Look familiar? So if you have a line on the coordinate plane, your rise is this part here, and your run's that part down there. And the slope is the ratio of the rise over the run. Same goes for a nonlinear continuous function, except it's not a slope so much as it is a relative rate of change. If y changes so much, x changes so much. And it changes based on where you are in the function. It's going to be different down here versus what it is down here, what it is here. That's why we have a function for the derivative when it's a nonlinear function. So there are two big things that we're looking at in this unit that relate to this whole dy dx thing, rise and run. The linearization is basically the tangent line, and we use the linearization to make approximations of different points and how fast a function is changing to get approximate values of a function along the curve. So we have the slope at a given input value multiplied by the difference between x and that given x value, how far away. If this is small, you're going to get a good approximation, plus the output at a. We also have Newton's formula, which kind of uses this concept of tiny bits of rise over run to approximate the roots, the x values where a function crosses 0. And that's equal to one approximation minus the y value of that approximation over the dy of that approximation. And then lastly, there's differentials, which we use to solve related rates problems. So if you have some function, y equals f of x, then the derivative of the y side, dy, is equal to the derivative of the f side, f prime x dx. And all this is just about how we've got the rise and the run kind of isolated from each other, and because we've got them isolated, we can look at them separately so we can compare the rate of change of one variable to the rate of change of another variable in a given situation. That's pretty much an overview of what differentials are and how they get used in this unit.